Okay, practice midterm. Wanted to give you guys an Adams take on that. Let's see how this goes. Okay, so we have number one, g of x and h of x. They say find g of -1 minus h of -1. If I saw that, probably what would go through my mind. It'd be something like, well, first we could find g of -1. We'll shoot a -1 into the 4x plus 5. 4x plus 5 should be like 4 times -1 plus 5. And then we'll do the same thing for the h in a second, and then 4 times -1 plus 5 is -4 plus 5. -4 plus 5, that'd be like a +1 by the time we're done. So there's the g of -1 part. And then the h of -1 part, that's -1 getting shoved into the h function, that'll be 3 times -1 to the third, just shooting a -1 into all these places, plus 2 times of, I put an x, sorry, -1. Okay, run a number there. Sorry, it's getting all crowded. I'll erase this stuff as we go. -1 to the third is going to be -1 times -1 times -1, ends up being negative again. So that ends up being 3 times -1 is -3, plus of 2 times -1 is -2. So we have -3 plus -2 is like a -5 or something like that. And then, or something like that. It's -5. And then we have g of -1. We got an answer for that. H of -1 got an answer for that. And now they're asking us to minus the two answers. And so here we was 1. The answer to h of -1 was -5. Outing here, looking good. And then I'm supposed to, I have 1 take away -5, or just 1 plus 5, because you got negative is like a plus. And so that's 1 minus -5, or just 1 plus 5. That's negative, or that's -1. That's number 1 for us. Okay, next one up. Number 2, well, whatever. We'll leave the dot on there maybe. Okay, number 2, we have g of x, just asking us to plus the two functions as is. And so here we go, just saying, keep it in general form. And so g of x is x thing. And so I guess we'll just plus them. So, okay, here comes the g of x plus with f of x, -4x plus 4. Beyond that, I mean, it's pretty much done. We've plussed them, or added them, if you will. And see if we can, like, simplify it, I guess. And x minus 1, you could call that a or like a 1x if you like. That. But this plus and then the parentheses thing seems to, like, I don't know. How do we say it? And so if we say, I don't see the parentheses really, 4x plus 4. And you can even just call it minus 4x. Anyway, from there, I'm looking at, here's a 1x, this 4x. Probably those we could put together as like terms, just 1x and a minus 4x. And so that's a +1, and a -3x or minus 3x. And then we have, for our constant terms, +4, putting those together. In that case, it's another 1 and 4 thing, but of course, that's a +3 on those. And that's about as good and simplified. Okay, on number whatever we're on, 3, f of x over 4. So a lot going on in there. Number, and that's whatever problem. But then they also have function of x. You could even think of it as being shot into the x in different orders, if you like. What I might recommend here is, as in, let's do g of x plus f of x, as functions. Shoot in x over 4 every time we see an x. Although you don't, and so you could put the x over 4 in right away, something like that. Got it. Plus with 3. Good. Not a lot of like terms action going on there, although there probably will do that. So like on the last one, maybe don't really need the parentheses. It's nothing, a positive one distributing in, it really doesn't do anything. -4, and now we have a +4 and a -4, and that's convenient for us. 0, so we have x squared plus 3x still, and then plus, or probably just don't bother to put +0. And now we have x squared plus 3x is kind of the combination of the two of them. That's not that. And now we can say now we'll do the x over 4 part. And so now we'll shoot in an x we'll put instead is x over 4. And so now here we go. Hey, over 4 instead of x squared, we'll call it x over 4 squared. Times not x, but x over 4. And then we just kind of that too, beyond that, it's whatever the heck we can do with this mess. So x over 4 squared, remember that's x over 4 times another x over 4, I guess. And then, whatever happens with that. And then 3 times x over 4, that's like a 3 over 1 times x over 4. And so that'll make for a nice product if we kind of put it as a 3 over 1. That might help. So then let's see how this goes. We have x times x is x squared. 4 times 4 is 16. Looking good. 3 times x is 3x. 4 times 1 is just 4. And then that's pretty good. Now, I'm having worked with this curriculum before, there'd be different ways of writing the answer. And so this would be something that I'd be probably tempted to leave it as. The fractions don't really reduce anyway. Looks pretty good. Something similar to this anyway. But depending on what direction you want to go with it, it might go a different way. So I was looking at this, and the answer key guy for this one, the guy that developed the software here, he decided to make them all as one big fraction. So that's what we'll do too. And so if we wanted to make those bottoms match, we'll make the denominators match. I could times this by 4 down here, and that'll make these both into a 16, 16 and 16. And then don't forget to times the top, and we'll just see what happens after that. Let's see here. Back to the old blue. Oh yeah. Then let's see here. I guess we know that it's something over 16, and this is over 16, so it's whatever, but it's over 16. And we didn't do anything to this one, so it was already over 16, so it's still just x squared plus, and then we have 3x times 4 would be like a 12x, I guess. And that's another way that this, it's another equivalent form, and that's what you're probably looking for from answer key guy. So looking pretty good. X squared and 12x over 16 won't get any better than that outside of putting it back to something similar to what we already had. Okay, let's see. Clearing them up. Looking good. Okay, next thing up, let's see. Let's see if we can scroll this mess. There we go. Oh yeah. All right, now number 4. It's a graphing deal. I guess these next few all are graphing deals, and so whatever. Okay, starting with number 4. There we go. We got 3 phases here. There are x inputs that are less than -1. Then there are x inputs that are between -1 and 3. Then there are x inputs that are bigger than 3. 3 phases here. And so I guess we'll shoot these things in there in 3 phases. Maybe we'll even color code it. So if we go green phase or something, x inputs that are less than or equal to -1. Well, if we shoot in an x that's less than or equal to -1, interestingly, the output also just keeps on being -1. There's nothing to plug into. It just kind of is -1. And so let's see here. We'll kind of record a little bit of what that'll look like. Hey, buddy. Okay. If we were to go phase 1, input, output, x inputs, y outputs, like we do. And we're like, okay, I'll shoot in x inputs that are less than or equal to -1. Well, that sounds like -1, -2, -3, etc. -4 and -5 and 6. Anything less than -1 is fine. And notice that equal to -1 counts. So we'll remember that gets colored in when we shoot in the -1 there. That'll be a solid or whatever we call it. And so then what we say in this phase, though, is that the outputs are defined as you don't plug anything in like you would in the other phases here. There's no x involved. The output just is -1. So you plug in -1, you get out -1. You plug in -2, well, oh, you get -1. Oh, we get, oh, it's -1 again, you know? And so then it keeps being -1. So that's what these inputs and outputs look like. Is we said, well, okay, if I shoot in a -1, I get out a -1. And so there's my X and Y there. I shoot a -2, I get -1. -3 gives -1, and etc. They keep on giving -1. And so we have this pattern where the line's just kind of going, keeps on being -1. And then don't forget, big part of this is that there is an equal to on my -1, not just less than. So then we'll say when we get there, that's a colored in circle there, looking good. Okay, phase two, we'll do it in some other weird color. Okay, there we go. X, Y, in, out, whatever. Okay, phase two, we're shooting in inputs that are between between -1 and +3. Oh, excuse me. So so then I guess let's see what that looks like. Between -1 and +3, well, it'd be -1 and 0 and 1, 2, 3. Pretty much, you could just do them all, I guess, if you wanted. You don't have to do all these, but that's the whole gambit as far as integers go. And then do remember, we have to be bigger than -1, but there's no equal to -1 on that part. So then with the -1, we're going to remind ourselves that part is an open circle. Don't color it in. When you get to the 3, equal to 3 does count. So then when we get there, we'll remind ourselves to color that one in. And then let's see what the outputs look like. For inputs that are between -1 and +3, the outputs look like 2 times something -4, or 2 times that number -4. So let's just see how that goes. This again a little messy. We'll clear this up when we get to number 5, but we'll go 2 times these numbers, then -4. And so 2 times, and then we'll do -1, I guess. 2 times -1 -4, that'd be -2, take away 4, which is -6. Oh, yeah. And then we got 0. That'll be even better. 2 times 0 -4 is good. Whatever that is. That's, well, I guess that's 0. 2 times 0 is 0, and then -4. So now we got -4. And then, we're just killing it now. Here we go. We got 2 times 1 -4. Something. 2 times 1 -4 has to be 2, and then 2 take away 4. 2 take away 4 is like -2, I believe. So then that'll be -2. We're on such a roll, I'm going to do these last ones. 2 times 2 -4, That's a cool one because it's 4, and then 2 by 4 minus 4 gives you a 2. Indeed, that's very good. Or, of course, approach. It said my internet was unstable. I hope the kind of my input and output approach. It's okay if you want to do some kind of an mx plus b thing. I always talk about that too. But if I shoot in -1, I get out a negative. I didn't mean to put a check there, so that's interesting. Okay, but a -6. And then if I shoot in a 0, I get a negative whatever it was, -2. And then a 2 gives me a 0, and you can see how this is going. And then 3 gives me a 2, and we got ourselves a good enough pattern set up. And then we just got to remember, when we plug in that -1 and we got that -6, that dot doesn't count. So we open circle that. But when we plug in the 3 and get out the 2, that one does count. Oh, yeah. Okay. And then phase 3, I might have to clean up some of this mess because it's getting so messy, but we'll just see. Okay. Phase 3, we need a new color here. Maybe we'll do blue again. Okay. Phase 3. This is for inputs that are bigger than 3. Input x's that are bigger than 3, and we shove them into this -x plus 1 mess. So let's see here. X, Y, input, output. Inputs that are greater than 3. I'm going to go ahead and put 3 there, even though secretly we know that 3 doesn't count. Really, it's 3.001 that counts, It has to be greater than 3, not equal to it. Anyway, 3, and then 4, and then 5, and 6. This way you have your kind of your start point. We call it a limit point. It's whatever. But do remind yourself that 3 doesn't count. So we're going to open circle that. And then 3, here we go. It's negative x plus 1 every time. So this would be negative of 3 plus 1. Negative 3 plus 1 ends up being whatever. Negative of 3 plus 1, that'd be negative 2. And then we just keep going. Negative of 4 plus 1. And that's negative 4 plus 1, of course, is negative 3. And negative 5 plus 1 would be something, negative 4. And then negative 6 plus 1 is negative 5. And looking pretty good. And here's the thing. We don't have to stop there. This is for any input that is bigger than 3. So we were like 3, 4, 5, 6, da, da, da. And just kind of I dot, dot, dot it with the ellipsis thing, whatever you call it, to remind myself that when I get through with these dots, I'm not done. They would keep on going past that. And so then 3, 4, 5, whatever, here we go. 3 gives me a negative 2. And then, so that's right there. And then 4 gives me negative 3, something like that. 5 gives negative 4. And then, so whatever else, 6 gives the other thing. And then 6 gives negative 5. And then we got a pattern that's going, but it doesn't stop there. It just keeps on keeping on past the 6, And so then past the 6, 5 thing. Looking good. And then we'll remind ourselves, oh, with that 3 that we plugged in, does it count? Does it not? And in this case, it does not. So leave it open circle. Don't color it in. This would be kind of, this is what you're looking for on the test. It's multiple choice. Do remember they may have 2 graphs on there that are the same picture, but one of them has the right dots colored in and stuff, and the ones that are open and stuff like that. Whereas the other one, you might have one that's the same picture that does not have that. So do watch out for that. Okay. Probably we should clean that up. There we go. Clearing them all off. Giddy up. Okay. But that's a pretty long-winded graph. These other ones, they go pretty quick. So here we go. G of x equals x plus 2 squared, take away, or sorry, plus 1, something like that. I would look at that and be like, okay, new 0 is negative 2 to make zeroed out, Here, we need some number, and when I say zeroed out, I guess what we mean is to make a 0 happen. So you could end up with a 0 squared, And so if I'm looking for that, then we'll be like negative 2 plus 2, negative 2 zeroes that out. So then if I were to look for like a good starting point, we call it the vertex point. A good starting point here, we'd say, oh, probably I'd shoot in a negative 2 because that gives me a 0 to deal with. And then 0 squared is 0, and then my output would be 0 plus 1. Or in other words, you shoot in something that zeroes you out, and then you just end up with plus that much as the output. Or some of you guys might remember, I undid too much. I'll try and erase that. I don't know. Who cares? But anyway, why would I erase it? It doesn't matter. Anyway, so then what is another way of looking at this is, well, this is like a left and right adjustment, but it's always the opposite of what it looks like. Adjustment or plus 1 means up 1. That also does work. Anyway, negative 2 and up 1, and that'll be the vertex point or a bit to this grows. And then from there, guys, we'll say, well, since it is quadratic, it'll behave like quadratics do. And we'll do something like up 1 over 1 and up 1 backward 1, and then like that. That'll be pretty much good enough for what we need. And do watch out if on here, that'll mean you're upside down. But besides that, it's pretty much we got. Okay. And then number 6 would be something very similar. And so we can do that one even faster. Here, I'll scroll. And then the drawings stay. Okay. All right. Let's get that done. There are the drawings. Okay. So then from there, we'll be like x plus 3 squared minus 1, same kind of thing. Negative 3 plus 3 is what zeroes that out. So we'll go negative 3, negative 1, 2, 3, and then it has a minus 1 instead of a plus 1. So that'll be a downward 1. Negative 1, 2, 3, and then downward 1. Boom. And then since, again, it doesn't have a negative number timesing out in front or anything like that, it won't be upside down. It just happens to have started from down here. And so it'll be up one, over one, up one, backward one, we'll say, and then kind of get steeper after that. We can always talk more about what patterns exactly it takes, but whatever. Anyway, looking good. And then from there, we have this one. Not really sure why there's not a graph provided for this one, but we'll go with it. G of x equals 3 times the square root of x. What I would do in a situation like this, because you're dealing with multiple choice and there'll be a bunch of like square root looking graphs or whatever. And so I would probably just, well, obviously I got to get a graph going here. You won't need to do that, but I would get an input output table going. Okay. So then let's see here. Input output table, X, Y, input output, something like this. What I would probably do is start shooting numbers in and just seeing how it goes, old fashioned way. I mean, there's other ways to do this stuff, but they give you such small graphs to work with on there. It can be hard to be super certain without having some data. And so I would just start shooting in numbers that are small enough to work with that would fit on the graphs they give you. You don't have to do tons of them, and then some of them will work better than others. So we're square rooting things, 0 and 1 and 4, they square root pretty well. Other numbers don't. And so that's where this gets a little fuzzy. And so, well, if we got to skip some, we will, or you can always calculator things. Anyway, so now we got, if I plugged in a 0, the square root of 0 is 0. And then 3 times that. So 0 there, 3 times the square root of 0 is 3 times 0. So that's nice. So 0 gives 0. Good. Then if we plugged in a 1, that's 3 times the square root of 1, which is, well, the square root of 1 is 1. So 3 times 1, and that's 3. That's good. And then we square root of 2 in a second here. I'm going to go ahead and erase this mess. Okay. If we square root of 2, 3 times the square root of 2, that's ugly. The square root of 2, as I remember, is a little bit over 1.4. And so then 3 times 1.4, that's kind of weird, right? It's 4.2 something ish. Feel free to calculate that, but it's a little bit over 4, not quite 4.5 if I remember right. Ugly. And then same thing with here. Let's just, before we erase it, we'll do the same thing with the square root of 3. I think that's a 1.7 or something like that. So then 3 times 1.7, that'd be like around 5.1 ish or something like that. 5.1, 5.2. Okay, those are ugly. You don't have to know that stuff, but just I would calculator it, and you'll get more accurate than my weird estimates. And then from there, we'll do a few others. Square root of 4 is a nice one. You'll probably want to skip to that one if it's a benefit, because really sometimes you can get by on just doing the nice one. 0, 1, 4, those ones all square root well. And that might be enough info for you, really. And so if I did a square root of 4, 3 times the square root of 4, that's of course 3 times, well, the square root of 4 is 2. 3 times 2 being 6. Now we got 4 gives us 6, and that'll be an essential one to look for. So even if if these ones are too ugly to get on the graph, you can certainly, probably what would be the most benefit to you would be doing these bigger, nicer ones. We have 0, 0, 1, 3, and then 4 gives 6. So in sum, this one looks something like we got 0, 0 going off. 0, 0 gives 0, and then 1 gives a 3. So we'll have a 1, and then 1, 2, 3. And then ugly ones, and then a 4 gives 6. And so we're like 2, 3, use them if we need them, and then 4 gives a 6. So then 1, 2, 3, 4, 5, 6 would be somewhere up there. Then you end up with this all tall version of the square root function. And if you keep on going, of course, it'll be, keep on what like they do. But something like this. And then on the test, you'll probably see different options that are like this one's there and this one's all like that or something. You never know. So always look for the ones that hit the dots that you got, because you'll have similar looking graphs, but you want to make sure that yours goes through these points, the ones that you found. And if you got to resort to using the ugly ones, then go ahead and do it. 2 should be up at a little bit over 4. So 2 and then 1, 2, 3, here's 4, here's 5. So a little bit over 4 somewhere up there. Although I missed on my curve, it looks like something like that. Anyway, that'll be pretty good for those. And then let's see what else. Let's clear that junk out. Okay, next deal. We got scroll this mess. Okay, number 8. That'll be a good thing to go over at 9. Okay, there we go. Where is the stylus? We do not know where it is. Draw. There we go. Okay. This one we have a square root of negative x. Remember how that goes. I mean, we can show you that you're always free to do, x, y, in, out stuff. Just, I mean, feel free. There is an issue with taking square roots of negatives. Since this is an Adam's take, I probably won't go one plugging in numbers like 1, 2, and 3. We're gonna have problems because then you're square rooting it, and a negative of that 2 won't go well, and a negative of the 3 won't go well. On, oh my goodness, my Google Home's going off. So then we're like, well, okay, if I can't do any of my normal numbers because it's making me to take square roots and negatives, I guess I could try negative inputs, and see if that cleans up the situation. Check this out. What if we started doing negative 1, 2, and 3, and 4, and whatever? Again, 2 and 3 don't square root very well, so I might actually just skip to 4, but whatever. We'll see if we need them. And then we'll be like, okay, if I had a negative 1 and I shoot it into a negative already square root, it will be like a square root of a negative of negative 1, and it's working, and so that'll be a square root of regular 1 gives 1. And so then that tips you off right away as you're like, okay, I plug in a negative 1 to get out a regular 1. Got it. And of course, a 0 will probably give 0 no matter how the negative goes. So it's probably there. And then let's skip the 2 and the 3. And then 4 square roots pretty well. So if I do, pretend like I wrote a 4 there. There we go. No, that's a bad idea. Okay, we'll shoot in a 4 and we'll do a negative 4. And then we'll be like square root of a negative of negative 4. And a minus minus 4 is a regular 4. Square root of 4 is 2. And so now notice though that we had to shoot in a negative 4 to get that to happen. Like we were talking about. 2, 3, 4. Shoot in a negative 4 and then you get out a 2. 1, 2. And then we got this square root that's going to the left because we had to shoot in negative inputs to get ourselves positives to square root. All that to say, that I didn't mean to really go into that much detail on that. But all that to say, if you have a negative on the inside, it's going to shoot you to the left. You might remember from your homework, you reflect to the left. If you see a negative on the outside, just in case you get that kind on your test or something like that, I'm all stumbling over my words. A negative on the outside of a square root, that'll actually reflect us downward instead of to the left. And so when our normal square root guy would be somewhere over here, you would see it square rooting downstairs or something at that point if you had a negative on the outside of the square root, because stuff on the outside is more of an up and down output thing. Anyway, that is all with that. Okay, next up, let's see how orange shows up. That kind of works, I guess. Okay. If we had an absolute value here, excuse me, g of x is absolute value of x plus 1. Remember how that goes. I can new 0 this, and then you don't have to do this, but it might be a benefit to be like, well, what's the outside, up and down adjustment? Well, it's nothing. And you can put plus 0 to remind yourself that there's no up and down adjustment in that way. And so negative 1 plus 1 gives me a 0 inside. So my new 0 is negative 1. And then up nothing, so I don't go up any from there. So negative 1, then up 0, and then it looks like absolute values look. Absolute value functions are kind of straight lines unless you're given something other special mess inside of the absolute value. And we end up 1 over 1, up 1 backward 1, slope, kind of V'ing it up, up 1 over 1, up 1 backward 1, continue. That's good enough for that one. Okay, let's see what else. Let's clear all that mess out. Starting to scroll in now. Okay, number 10. Looks like I'm not going to fit both of those in there, so we'll just do number 10. Excuse me. Approximate the intervals where each function is increasing and decreasing. Okay, something like that. Let's get back to the pencil there and we'll choose a color. Something like that. Notice it's, if you're reading from left to right, it's somewhat comfortable to be like, it seems like it's downhill, then it's uphill, then it's downhill. And so then quick reminder on this without, again, I'm going to try and go fast here. without overdoing it. We can always get more into the details of why this does the way it does, of course. But it looks like here's a splitting point right here, and a splitting point right here where it stops going down and starts going up. And then, oh, right here is where it stops going up and starts going down. And so those would be pivotal points to notice, pivotal moments. And that's the thing I wanted to emphasize real quick is remember your pivotal moments when they're talking about where is this thing increasing and decreasing, they're talking about the X values. It's like a timeline thing, like when in history was this happening or something. And we're like, well, okay, somewhere everything's going fine and it's downhill, downhill, downhill until wherever that was. They don't want to know how far down it was. Don't tell them -7 or something. Tell them when on the X line that happened. And so I guess what we'll say is it starts out with a decrease. Started out as a decrease, we're downhilling forever. And we'll say it's been from forever in the past. If we're just thinking about X values and we're just analyzing the X line, it seems like this function has just been downhill forever until it got to the middle of the graph. And the middle of the graph is where it stopped going downhill and started going uphill. So we'll say it decreased from forever in the past, -infinity, until it got to the middle of that graph. And so that's what we'll say. Pretend like this is nice penmanship, I suppose. We say DEC stands for decrease. And we'll be like from -infinity all the way until, well, middle of the graph is an X value of 0. Just focusing on the X's again. And then from there, it looks like it's uphill for a little while. So I'll change colors to emphasize. Now we're uphilling from the middle of that. Is it not changing colors? We're uphilling from the middle of the graph until we get to about right wherever the heck this is, a little bit past 2.5 ish or something, on the X line again. And so I guess that's what we'll say about increase. We see an increase from the place where we left off, which is the middle of the graph, or an X value of 0, until about, yeah, 2.5 ish, 2 point something, we'll say about 2.5. And that's where it started going downhill again. So we'll say, okay, done there. And then we're back to decrease again. So then change back to blue thing here going on, change color. And we'll say from that 2.5 line until forever after it's decreasing. And then remember, if we're talking about X values, that's from here till forever after to the right. And so I guess that'll be our other decrease part is we'll say it decreases again from that 2.5 until forever after infinity positive. And you can union those two things together. I think the way that they have this question phrased, it's okay to just put commas between them is the way they have it in answer key guy. It's whatever. Cool. All right, number 11. Yeah, let's clear that junk out. Okay. We'll get this thing scrolling. Okay, number 11. Let's get the graph of the function. If I saw that, probably I would just, okay, something like this. There's different ways of doing it, really. Since it's quadratic and it's in standard form, okay, here's a couple of things that come to mind. If you're desperate, you can always just kind of shoot in numbers and be like 0, 1, 2, 3, 4, and then, do as many as you need to until it eventually starts taking shape, that also works. And do a bunch of negatives and stuff, -1, -2, -3. I kind of hate doing that because how long it takes, but you can always do that if you're desperate. Besides that, remember there's different ways. By the way, if you prefer to do some sort of like an ABC thing and it's like the -b/2a or something that video guy did, don't worry about it. You can totally do that. It's totally fine. And it's a pretty fast way to do it. What we have always done in class is something to the effect of like, okay, if I could just kind of get an old 0 and a new 0, X, Y, input output, and I'll find, I guess the process is I know it's going to be some kind of a parabolic shape. And so if I could just find two dots that are next to each other that have the same output Y value, then right halfway between them will be my vertex, And so that's what we'll be shooting for is to find two dots that give me the same Y value output, two matching dots on the left-hand side and the right-hand side of this parabola. And then right between the two of them will be our turning point vertex. Okay. So here, let's clear that junk out. Okay. So that being the case, probably the easiest way to go about that would be I'll just shoot in a zero at first because 0 squared and 16 times 0 minus 27 just gives you negative 27. And you're like, well, negative 27, I don't really want that for an output. And it'll be okay. Because then now we're like, okay, if I plug in 0, I'll get negative 27. Now I need to figure out if I can plug in a new 0 that'll also give me a negative 27 out. Because if I can do that, then when I split the difference between wherever these points are, halfway between these two dots, 0 and wherever else, halfway between them, that'll be my vertex there and it'll be perfect, That'll be good. Okay. 27 and a half about that. Boom. That. Okay, good. Then okay, if we just focus in on these two first terms and then just preserve the 27, then okay, if I can new zero my way to that and find a way to get those to zero out besides just plugging in a zero, that'll be perfect. And so focusing in on that part, negative 2x squared minus 16x, I'm hoping to get that to be a more friendly way to find out how to zero that. And so ignoring the 27 for a second, I'll go ahead and write it there. But I'm going to focus in on these other two terms here. Noticing, though, look at this. If I could find a common factor between the two of them, something that goes into both, and I could maybe divide that out or factor it out of the two, that tends to be a good way for me to be able to see the new zero I'm looking for. And so check this out. Now we'll be like, okay, these first two terms, they both got an x. So I'll take an x out of both at the very least. And it looks like 2 goes into both. So I'll divide out of 2. Since that's a negative there, that's really bothering me. Probably I'll divide out the negative also. So divide out a negative 2x from both of those first two terms. The 27 is just sitting there. And then now let's see here. If I divide negative 2x squared, divide negative 2x, I have just the other x there. And negative 16x, divide negative 2x. Let's a negative divide negative. That's a positive. And 16 divided by 2 is 8. So 8, I guess. And then x divided by x is, well, no more x's. And by the time we're there, I can see my new zero. If I just shoot in a negative 8 plus 8, that'll be 0 in this out. So negative 8 will probably do it. Because then if that's 0, then 0 times whatever doesn't really matter. It'll be 0 still. And then 0 minus 27 gives me my 27 out. So I think that negative 8 will do the trick for me. Let me clean that up a little bit. And now looking at that, we'll say that negative 8 is my new 0. Boom. And that's perfect for us because remember, we said if I can find two numbers or two dots that are on the left and right hand side of this thing that match, then right halfway between them will be my vertex. And now I think I can find it. Halfway between 0 and negative 8. Well, that's easy enough. That's halfway to negative 8. That's negative 4. Or just half of negative 8 pretty much is all you need. And so negative 4, and then that becomes my input. And then how do I find the output except, well, I'll shoot in the input, So that's where we'll say negative 4. I'll use it as an input like we normally do, and I'll shoot it in for the x's and see how that goes. I don't know if you guys can hear, but they're warming up for the air show out here. And so hearing all these jet engines out here, I don't know if you can hear it. Anyway, so I'll shoot in the negative 4 and say, here we go. Negative 2 times, and then it'll be a negative 4 squared minus of 16 times of negative 4 again, and then minus 27. And we'll see how that goes. Hopefully it's not going to be gigantic because they have this tiny graph. And surely we should be able to at least find the vertex on there, or else they maybe messed up their graph stuff, And so negative 4 squared, that's a positive 16. So the negative 2 times of that positive 16 we'll figure out. And then we have minus 16 times negative 4. We'll figure that out. And then minus 27, just taking care of the squaring part first, And then from there, negative 2 times 16 is negative 32. Negative 16 times negative 4, that's a double negative. Negative times negative, so that's a positive of 16 times 4, which is 64, and then minus 27. Interesting that this is twice as big as that and that they're opposite signs, but that is kind of the nature of that being to a negative thing. Anyway, negative 32 plus 64, that's like a positive 32 by the time we put those together, minus 27. 32 minus 27 should be 5 if I remember right. And so then now we have -4 gives 5, and that's perfect for us. -1, 2, 3, 4 gives 1, 2, 3, 4, 5. There is our vertex. And then we'll just look up here for hints about it so we don't have to keep getting a bunch of dots. For one, we knew that our other points were at -27, so they got to be down here. It's not going to be going up. It's got to be a downhill one because how else are you going to get to those -27 outputs way down there? I don't think so. So it's definitely a down anyway. But if you hadn't noticed that, -2x squared does indicate that we have a negative going on for our, on our lead term, and that's going to be a down 2/1 for our starter slope. If you want to be real particular about it, but at the very least, if you see a negative here, it means we're going downhill. Downhill, and our starter slope is down 2/1 because it's a 2/1 thing. Anyway, that's pretty good for that one. Let's see what else we got. We'll clear that out. Boom. Okay. Come on now. All right. Now we've been scrolling. Here we go. Finding x-intercepts and stuff. Let's the x-intercepts where the graph crosses the x-axis and then sketch it. Looking here, we're hoping that this is factorable, and it looks like it is. If you quadratic formula thing, but if we had this and it looks factorable, we can 9 that add up to -6. That looks like -3 times -3. Now we could say, well, I can zero this out and find out. Just say, okay, x values that give me intercepts do, an x-intercept is where the y value is 0. So I'm looking, and so if I saw this, well, 3, but then again, we have +3 for the other x-intercept. One of them is at 1, 2, 3. The other one's at 1, 2, 3. So that means for us is, okay, this is a quadratic graph. We know kind of how they, and oftentimes they'll hit the x-axis at 2 different spots because this must be a touch point, as they call it, because it's only hitting it the one. And you might remember things about zeros too. We're going to say, okay, it shoots down. I kind of missed the axis there, so we kind of pretend I didn't miss. Bounces off, which is typical when you see 2 of the same 0 there. And so we'll arrows at 3 with a multiplicity of 2 because there's 2 of them or something like that. There are x-intercepts where it crosses through the x-axis, and we didn't cross it. So we'll say there are no x-intercepts where it crosses the x-axis. None of that. Although we do have x-intercepts. They just don't cross it. And then can I draw a picture? It looks like we did. It's an uphill quadratic. So it would go, u up, if you will, instead of the n downward. And then it hits at +3. And so since it hits nowhere else, it must be doing this. Looking pretty good. Okay, next one up. On number 13, we have a quadratic inequality. Not real obvious that it's quadratic, but it is. And so let's see here. Boom. Okay. Quadratic inequality, we're saying I need to figure out what inputs I could shoot in for x so that I get an output that's greater than or equal to 0. I guess I'll pick up the pace a little bit because I've been over explaining some of these, and you probably want a fast take on some of this. And so if we did, or maybe not, maybe you don't want that. I don't know. We'll see what we can get away with. Something that seems a reasonable pace. First, I would shoot for what makes this thing equal to 0, And so if I were to say, well, what makes it equal to 0? 4 minus 4 makes equal 0 happen. So x equals 4. And again, 1 minus 1 would make it equal to 0. So x equals 4 and x equals +1. These ones make it equal 0. And equal to 0, you notice, actually does count. That is part of the solution here. It's not always, but sometimes it is, and this time it is. Okay. So they make it equal to 0. Then what you might remember is from there we'll partition our number line into different categories. We have, here's the number 4, or here, I guess if I put a 0 there, just to kind of give reference for our number line where the middle of it is. Here's the number 1 somewhere over here. Here's the number 4 further over there. So they're both positive. And then we'll say, okay, what about all the rest of the numbers on the number line? Do they do what we want them to do? And so where are on that number line numbers in, like a number here or there or wherever else? Which numbers could shoot in here so that the output is greater than zero? Equal to zero, we already have covered because we found the equal to zero ones. The greater than zero ones we need to find. And it's hard to know where there's going to be. So we actually just start trying stuff. And so notice though that equal to zero does count. And since these things make it equal to zero, we'll go ahead and color them in. And then we'll try numbers that are on the right-hand side and the left-hand side and in the middle of this number line as representatives. So if I were to try some number that is to the right of 4, I could say, well, maybe I'll try 5 or 6 or 7. Some number that's between the two of them, I could try something between a 1 and a 4. You could try a 2 or a 3, obviously. And then if you wanted to try something to the left of 1, anything to the left of 1 is fine. 0 is probably my favorite because it's just right there and it's the easiest number to do. But you could do -1 or -10 or anything you want. I'm going to try 0. And then when I say try them, we're going to go ahead and shoot it into the inequality and see if it gives us what we want. Does it give us a greater than 0 output? Remember what greater than 0 looks like. It means it'll be positive, you know. Do I get a positive output out of this? Probably I won't get equal to 0 because we got that covered. Okay. So then here we go, trying 0 again. Or sorry, not again, but trying 0 on the left. 0 minus 4. See how that goes. 0 minus 4 times 0 minus 1. And we'll just see if that goes well. 0 minus 4 is -4. And 0 minus 1 is -1. Timesing those to each other. And here's the moment of truth. They're both negative. And a negative times a negative is a positive. Obviously, 4 times 1 is 4, but more importantly, this is a positive, which means it is greater than 0. So this is good for us. So now we'll say numbers to the left here, they do actually do what we want them to do. We tried numbers, and we tried a number to the left, and it showed us the behavior of those kind. Numbers to the left do what we want them to do. They give us outputs that are positive. So we'll color those in, then we'll try the middle, and we'll try the right-hand side. So if we try a 2, let's see here. We try a 2, that's 2, just plugging in again into this inequality, 2 minus 4, and then 2 minus 1, and see how that goes. 2 minus 4 is -2. See, this is telling because 2 will be smaller than the 4, but bigger than the 1. So we'll see how this plays out. 2 minus 4 is -2. 2 minus 1, though, is positive still. That's +1. So we have a negative times a positive here. And so that's going to be negative. And 2 times 1 is 2. It's whatever. But more importantly, a negative times a positive will not give us what we want. That'll give us a negative that is not bigger than 0. No, bad, not what we're looking for. These numbers don't do what we look for. Okay, then we try 5, same kind of thing. It'll be like 5 minus 4, and then that's a parentheses thing. 5 minus 1. Let's see how this goes. 5 minus 4 is 1. 5 minus 1 is 4. But 5 is bigger than both of those things. So they're both coming out positive both the times, you know? So that's the big part. It's a positive times a positive. It's still positive. It's whatever. And that positive means that it is what we're looking for. We're looking for an output that is greater than 0. Looking good. So numbers over here, they do what we want them to do. And that's how we'll state our answer. We'll say the things that we do what we want, what we're looking for is any number as far to the left as you want and as far to the right as you want, but not in between 1 and 4. But do count the 1 and the 4. And so it looks something like this in integral notation. Negative infinity all the way to +1. Count the 1. Union that with count the 4. And then go all forever after positive infinity. That looks pretty good. Okay, next one. If I saw this number 14 here, let's see here, clear this junk off. Okay, number 14, another inequality. It's also quadratic. Little bit troubling because it's not factored, and I hate the fact that there's a negative there. If there were no negative there, I'd just probably go straight into factoring the thing. You know, I hate that. And so, I mean, you could always do it with just treat it like a -1 and do something. What I'd prefer myself is I'm going to times both sides of this mess by a -1. Both sides of the inequality by a -1. And that will twist us up a little bit, but it'll make this a lot easier to solve. Now we got negative times everything. It'd be a regular x squared, then a regular 3x, then a regular 2. And then 0 times -1 is still 0. The only thing you got to watch out for is, remember, by times or divide by a negative, I'm backwards now. My inequality is flipped, so watch out for that. From there, though, this will become a lot easier to solve. Now we can just be like, well, okay, x times x, things that times the 2 that add up to 3 is like a 2 times 1, I think, and then we're looking for, well, what makes this thing greater than 0? Now we can kind of do it like we did the last one. So I'll kind of proceed fast on this from this point because it'll go very much like the last one did. And so things that zero me out will say, what makes it equal to 0? Well, -2 does that, -2 plus 2, and -1 plus 1. So -2 and -1 are input x's that'll make it equal to 0. And then we just kind of keep going. And so then here's -2 and here's -1, because if we made the middle of the number line 0, right, then the negatives are on the left. And so here we go. Does equal to 0 count? Yeah, we have an equal to 0 symbol there, less than or equal to. So equal to 0 does get colored in. Otherwise, don't color them in. And then we'll just start shooting numbers in. And you can shoot them into the original version of your inequality or into one of the newer versions we made. Any of it's fine. Although I'd be consistent in what you're doing so that we don't, make a bunch of weird mistakes because there's too much inconsistency. But boom, let's try this together. Okay. And we'll get rid of that arrow too. Okay. Almost there. Okay. So we'll try a number to the left, a number to the right, and a number in the middle, and see how that all treats us. I'm probably going to plug into this bottom version of the inequality just because we have developed that already most recently. And so here we go. A number to the left of -2, we could try like a -3. A number between the two, -1 and -2, that's awful. So we could try like a -1.5 probably. And then a number to the right of positive, or sorry, to the right of -1. Well, I guess if we're to the right of -1, 0 would work, That would be nice. So 0, 1, or 2, or some other fine number would be fine. Okay, there we go. -3. Now we go -3 plus 2 and -3 plus 1. Let's see if it does what we want. -3 plus 2, -3 plus 1. And then let's see here. -3 plus 2 is a -1. -3 plus 1 is a -2. Because -3 is bigger than both those. And so then negative times negative, that ends up giving us a positive, +2 in this case. And so that is what we're looking for. Because remember, though it was a less than 0 in the start, by the time we're plugging into this, we're looking for greater than 0. Although it will work if you want to shoot into this and look for less than 0. That'd be fine. We just don't have that extra negative to work with. So now it's greater than 0. Okay. Boom. Looking good. We're looking for stuff that's greater than 0 at this point using this version of the equality for now. And then we'll shoot things in between. -1.5. Let's see how that goes. -1.5 plus 2. -1.5 plus 1. Okay, -1.5 plus 2. That's like a positive half. Positive. We'll just put 0.5, I guess, or something. No, probably not a 2. 0.5. And then -1.5 plus 1, though, the negative being the bigger one there, this is a negative 0.5 at that point. And now timesing the two of those together, positive times a negative is a negative. And then 0.5 times 0.5 is 0.25, but that doesn't matter as much. It's the positive times the negative, which is a negative, not what we're looking for at this point. I'm looking for things that are bigger than 0, not negatives. And so then moving on, didn't work. And then we'll try 0, and that'll be our favorite one. 0 plus 2 is easy, and 0 plus 1 is easy. This is just 2 times 1 by the time you're done. They're both positive, and that's the important part. Positive 2, this does, because 2 is greater than 0, it's positive. That does do what we want. And so numbers to the right seem to give us the kind of outputs we like. And I say seem to, we can always talk about why it is definitely for all of them. Anyway, and so then now here we go. I guess we'll just characterize that and we'll say, okay, we got a solution set for that. from forever on the left until -2, a lot like the last one actually, until -2. Count eight, looking good. All right. Okay. Okay. Sketch the graph of the function. Come to mind for me. It will change colors or something, I guess. If I saw something like this, different ways you could go. You notice it's a cubic function, it's x to the 3 polynomial. That being the case, you probably wanted to get something super telling and accurate. But since it's not asking for and all that, probably what I would say is it's just puts in and just kind of get what you need out of it. Feel free to find zeros if you need to, but we're going to be doing plenty of that as time goes by. Excuse me, as time goes by anyway. So then you could shoot in a 0, 1, 2, 3, a -1, -2, -3, and do more than that if you need to. Go 4, 5, 6 on each side if you want, or out to 8, or do all the evens or something, and then just see how it goes. 0 squared, or 0 to the third, and 0 squared. Those are easy. And actually, that might be I'll show you a cheater's trick. We're shooting in zeros, we get -3 because it's 0 plus 0 minus 3. Or 0 minus 0 minus 3. And so that means our first dot is at 0 over and 3 down. And so what I would do, probably a good cheater's trick, is first off, see if any of the, you do a multiple choice, see if any of the graphs hit that point, if they go through 0, -3, or if they cross the y-axis somewhere else. And so watch out for that. We want the one where the y-axis, or sorry, the y-intercept is at -3. So watch out for that. Also be watching out for the fact that this is an x to the 3 function. So it's going to have 1, 2, 3 pieces to it. And that is a positive x to the 3. So it will be 1, 2, 3 ending on an up note, not 1, 2, 3 ending on a down note. So anything that looks like it ends on a down, don't do it. Or if it looks like 4 or 5, 6 pieces, something like that, don't do it. We need 3 pieces ending on an up. That's probably what I would start with. And then I would say, oh, okay, I got a y-intercept at -3. So if you see one of these things, it goes 1, 2, 3, and it's got a y-intercept hidden right there, looking gold. Doesn't mean this is the graph. It could be, for all I know. It could be 1 and then 2 and then 3, but it's going to be hidden right there, and it has the right shape. If that's not good enough to narrow it down for you in the multiple choice zone, all that, feel free to keep shooting in numbers there. And so then something like this, we go, well, okay, 1 to the third, 1 squared, 1, or -3, that'd be, well, 1 minus 1 minus 3. 1 minus 1 is 0. So then -3 again. That's crazy. And so then if I plugged in a 1, I would also get a -3. And now we're starting to see this thing take shape. Because the only way that it's going to have 2 dots next to each other is if it comes back for one of them. Boom, boom, bam. Or it could be something like wham, bam, bam. Okay. Anyway, it means we don't need a whole lot of other dots to get some shape on this. And so let's see here. If I plugged in a 2, 2 to the third, let's go ahead and do that one. 2 to the third minus 2 squared minus 3. 2 to the third is 2 times 2 times 2. So that's not 6. Be careful with that. That's 8. And then 2 squared is like a 4. So then we have 8 take away 4, take away 3. 8 minus 4 is 4. And then 4 minus 3 gives us a 1. So we shoot in a 2, we get out a +1, and it's starting to take shape, guys. And then you can, we'll feel free to do a couple more, I guess. And after a couple more, it'll be pretty clear to us what's going on here. I think I have a guess. It's probably something like this, and so we'll see. If we plug in a 3, let's see how this goes. If we can do it without getting all cramped and messy. 3 to the third minus 3 squared minus 3. Shooting those in there, 3 to the, oh, sorry, 3 to the 3. There you go. 3 to the second to the third. It's 27 minus 3 squared is 9 minus 3. Now we got 27 minus 9 is 18 minus 3 is 15. So now we got a 15 for an output. That means by the time we plug in a 3, we're way off the graph, way up here. So indeed, this is going to go straight, skyrocketing up from there. And that's probably enough info for us because now we got, boom, something like that going on. And if you feel like you need more detail than that, you can always plug in negatives, -1, -2, -3, and you'll find that you probably are getting dots that are somewhere down there. Cool. That's what I would do. All right. Layering it up. Number 16. Okay. Finding real zeros. Remember how this goes? We'll try and there we go. We're doing a different blue this time. Okay. We'll try and make this kind of painless if we can. Find the real zeros and state the multiplicity of any repeated ones. So by our whatever, our rational root theorem and all that stuff, we're normally like, well, whatever goes in the last term and whatever goes in the first term, that'll help you to narrow this down. And we will be doing that. We'll probably do that on the next one. Notice here, though, we don't have a whole lot of terms. Everything has an X on it. There's no like +5 at the end or anything like that. That being the case, I guess what that means for us is we'll be like, well, I noticed that I could plug in 0 and get out of 0, And so as far as an input output goes, I know it's kind of looking like a face and stuff, but for coordinates here, I can plug in a 0 and get out of 0. And so that actually tells me right off the bat a little bit about this. And so I'm looking at this, there's an x to the 3 function and it ends on a down and it's something like this 3 graph to look like this. And I'm noticing that if I might be able to do that more than once. And so here's a quick way to handle it. If you get a super, it's super simple compared to some of these more bizarre ones, but throw people. So if you see something like this, I would say, first off, notice what you're dealing with. It is an x to the 3 deal and it has a negative on it. So it'll end on a down. Now we have -x to the third minus 2x squared. What I might also do, because there's not like a constant term at the end to be able to do your rational root theorem stuff with or whatever, is factor out what you can. They both have a couple of x's to give here. Common factor be x squared, I guess. And so it'd be like x squared. And since that has a negative in front, I might even just take the negative out because it bothers me. By negative x squared, well, a negative divided negative is a regular positive. And then an x to the 3 divided out 2x's gives me 1x left. And then negative divide negative is positive again. And then 2x squared divide out essentially a 1x squared, 2 divided by, there's not really a number, so you could put 1. 2 divided by 1 is 2. And then x squared divide x squared it's enough to cancel itself out. No more 2's, or sorry, no more x's. That's looking pretty good. From there, what we notice is this. If I plug in a 0 into one of these x's, I get, it's just 0 squared. And that's where we start getting this mess, like we were saying. 0 squared is 0. And 0 times whatever the heck goes on here will still be 0. And notice that there's a couple of that, because there's x squared. That's kind of x times x sitting outside. Not paying attention to the -1 part because that doesn't really change anything. But we have an x times another x. Those are zeros that you could just shoot in there. And then the other factor, though, is an x plus 2. And that's nice because now we can see what zeros that out. -2 plus 2 will give me a 0 output there. So I have a 0 gives me a 0 here. A 0 gives me another 0. And then a -2 plus 2. -2 gives me a 0 also. So -2 gives me a 0 there. And now I can state the multiplicity and all that stuff. We can say, well, x equals 0 happened twice. So we would say multiplicity of 2. And then we also have an x-intercept or a 0 at -2. X equals -2 with no multiplicity really. And so it just, I guess that's how we'd summarize that. And then we draw a picture by making sure that it looks like it's supposed to look. Knowing that there's 2 dots right here, And so it makes it always a little bit weird when you got multiplicity like that, like we were saying a second ago. Like if we had three x-intercepts, three zeros that were in all different places, this would be easy. We'll make sure we got the right shape and we'll just hit them all down, up, down, boom, hit them. But when you have two dots that are on the same spot, then you're going to hit it, go something like this. This one will strike through it like normal, no big deal. Because we'll hit it on the up and on the down. That way it's got to kind of, and it's what we call a touch point, like we were talking about earlier. So we had an up hit and a down hit, and we're done. And then that way we're hitting all three of them, sort of. Cool. And it has the right shape and everything. Looking good. Okay, next one up. Oh, you know what? I'm going to clear that out and move this mess. Okay. Okay, next deal. But I saw this. Okay, for each function, list the x-intercepts where the graph crosses the x-axis and those where it does not cross it. That's kind of the things we are talking about already, but they're just more zeros to be found and some tougher things to do. Excuse me. So then let's see how this goes. If we say, let's narrow down our guesses, narrow down, using our, what do we call that? The remainder theorem. No, the other one, something, the remainder theorem, or at least a corollary of the remainder theorem that says narrow. So narrow it down a little bit. We'll say things that go into things that go into 9 over things that go into, I guess the first term is a 1 there, so into 1, and a plus or a minus of all that. That's cool because it's a pretty short list. Things that go into 9 is like 1 or 3 or 9, plus or minus of that. Over things that go into 1 is even better. And so then this is what our numbers will look like that are worth trying, you know, without getting into all the particulars of that. These are the potential rational zeros, as we call them. And so then here we go. We'll say we could try positive of 1 over 1. 1 over 1 is 1, and I'll try the positive version. So here's the 1. And then by synthetic division, we'll guess fast, narrow it down, then we'll guess fast. -1, then 7, then -15, then 9. And here we go, we're guessing. Drop it. -1 times 1 is -1, adds up to a 6 times 1 is 6, of course, and then adds up to, wouldn't you know, I think we got our first try. -9 times 1 is -9, and that adds up to 0. So we found one on our first try, and that's awesome. Okay. We know that this is an x to the 3 function now, so there'll be 3 solutions here, 3 zeros, be they real or rational or whatever they are. We found the first one, and what's left over here now is quadratic x squared and regular x, guys. So now we have a -1 x squared and a -6x and a -9, and I'm wondering what makes that equal 0, and we can get a factorization on that or whatever else we want to do. From there, I hate the negative out in front. You might also, I'm going to go ahead and times a negative on both sides. And then let's see how that goes. That means, sorry to spill into the next step. We have regular x squared, a positive 6x, and then a +9 now. All that, we're wondering how to get that to equal 0. And that we can factor out. We'll be like x times x. Things that times to 9 that add up to 6 is a 3 and another 3 again. And so then from there, now we have our other zeros, because if I want that to zero out, this is -3 plus 3 makes 0, and -3 plus 3 makes 0. So now we have -3 there and -3 again. Those are our zeros. And we'll mention that just like we did before. Because of the multiplicity, remember how that goes, is we'll say when there's a multiplicity of 2 of them, multiplicity 2 of these guys, these zeros that match, that means that'll be a touch point. That's not a place where it'll cross the x-axis. So we'll make sure to mention that. We'll say, I found an x-intercept where it crosses the x-axis, and then I found 2 of them where it does not cross the x-axis. And then so we'll just mention that, and then we'll say, for the picture, we have a -x to the 3. So that'll be 1, 2, 3 pieces heading on a downward, not 1, 2, 3 heading up. And we'll make sure we hit all these dots. And so we have, here's a 1, Here's a -3, and there's another dot right on top of it, also a -3, and that'll be the touch point. If I'm going to keep that shape, it means we're going to bounce off of the one and then come back to the other and be done. There we go. Hit it down, hit it again on the way up, and then come back through the other one. Looking good. That's probably how that would go, and these are your solutions. Okay, what else? What else? We got some division going on here. Okay, number 20. If I saw this and it said to divide it, I'd probably go synthetic division. So probably just because if you have a small enough, simple enough divisor, synthetic division will work well for you, and it's an easier way to go. So remember how that goes. Don't put the X and don't put the positive, put -4. And then we have a 2 and a 6 and a -6 and a -4, and just let it be. So now we have, excuse me, we have a 2 there, and then 2 times -4 is -8. 6 plus -8 is -2 times that -4. That's a +8. And then -6 plus 8 gives a 2. And then 2 times that -4 is, well, -8 there. And then -4 plus -8 makes a -12. That's our remainder. And here's our quotient, if you will. And remember, if we have an x to the 3 divide out an x, that gives us an x squared here. And then a regular x and then a 2. So we have essentially, here's our quotient and remainder, 2x squared minus 2x plus 2. And then we have a minus of 12 over our divisor as a remainder, x plus 4. In the homework, it just says do remainder 12. And this one, we put it over, the divisor. Okay. Same kind of thing on the next one. Interestingly, it's an x plus 4 there too. So that's weird, but whatever. And so then we'll do the same kind of thing and it'll go fast. And here we go. -4, and then 3, and then 7, and then -14, and then 26, and then -1. Loving it. Bring it down to 3. 3 times -4 is -12. Adds up to what? -5, I guess. -5 times -4 is 20. Adds up to a 6 times -4 is -24. Looking good. This is a 2. 2 times -4 is -8. Now these add up to -9, and there's my remainder. And so now this was an x to the 4 divided out an x to the 1. So then we'll say this would be 1 degree less, or x to the 3, So this is 3x to the 3 minus 5x squared plus 6x regular plus 2 minus of 9 over our divisor again, x plus 4. And it's okay to do plus -9 if you prefer that. I think in the homework in the test software, they're using plus a negative. They're using a minus, I think, instead of a plus negative. So they'll probably say minus, and then they'll do the 9 over the fraction. Cool. All right. Now, number 22. Here, let me clear these out. Number 22, we have a long division. Can't get away with this one, trying to do synthetic because the divisor is more complicated. So that being the case, let's do it to it. We have 3x to the second plus 5x minus 3 dividing into that whole other mess. 15x4 plus 19x3 minus 25x squared plus 6x minus 3. Okay. And then dividing that up, remember how this goes. The very first thing into the very first little bit will be a good divide. 15 divided 3 is just 5. And x to the 4 divided x to the 2 is x to the 2 left over. Just dividing this divide by the very first little bit, 15x4 divided by 3x2. And then 5x squared times all those things. Now we're in the timesing step. So here we go. 5x squared times 3x squared will be 15x4, as it should be. We're hoping those will cancel later. 5x squared times 5x, it'll be a plus of 25x to the 3. Yeah. And then 5x squared times -3 would be a minus of 15x squared. Then we're minusing it. And so remember, that minus is going to mess things up. 15 minus 15 is fine, gone. 19 looks like plus 25, but we know better. It's a negative. So then we'll be like, 19 take away 25 is -6x to the 3. And then negative 25, not minus, but plus, because it's a minus minus. So positive 15, negative 25, positive 15, that's a negative 10x squared. Drop in the next guy, 6x. Now, let's see here. First guy into the very first little guy. We have negative 6 divided by 3 is negative 2. Now we have negative 2x times all of those. Negative 2x 3. Negative 2x times positive 5x would be a negative. And then negative 2x times negative 3 was that positive 6x. Didn't see that coming. That's kind of cool. And look at this. Minus. And now we got same thing. I have negative 10 minus minus 10. That's, and then 6x minus 6x. Zero this, zero that, whatever. We got just negative 3 left over. And it's got no x's at all. There's no more x. Well, it's a lower degree than what we had to start with. So we'll say that must be over the x plus 4. Didn't expect it to go so. Okay. Least degree with the integral coefficients that has the given zeros. I'm going to go ahead and scroll. That they get ugly as you go. So check this out. Or to make a polynomial of least degree and all that, like they said, I would say f of x, and then, or you don't even have to draw it as a function and still get away with it, but that's kind of what they had in mind, polynomial function. Oh, they do say function. There you go. Somebody's paying attention. Okay. Let's say equal sign. I don't know, whatever. It says equals. Just, I don't know, I'm making it worse. Okay. But if we have a positive 2 as a 0, then we'll shoot an x minus 2 factor so that 2 minus 2 zeros it out. You know what I'm saying? And then now we have negative 2 there. We'll put an x plus 2 as a factor so that negative 2 plus 2 zeros it out. And then if I have a positive 5, then we'll go x minus 5 and etc. If you have more of them, then keep doing more of them. And then we'll pretty much just FOIL it out. And so if I were to you, there's a lot of ways to times this stuff out. If I were new at this like you guys are, I would start on the right-hand side and keep this guy on the left until later. And then we'd be like x squared, x times x is x squared, minus 5x, and then 2 times x is 2x, and then 2 times negative 5 is negative 10. Maybe put these guys together real quick, I guess. And then we have x minus 2 sitting there waiting his turn. And then this ends up being like a minus 3x, I think, if you put those together. And so then we'll say times x squared minus 3x minus 10. And then here we go. Now we got x times all of those. X times x squared, x times this, x times that. It's x to the third, and then x times minus 3x would be a minus 3x squared. And then x times minus 10 is minus 10x. Then we have negative 2 times everything. So we got negative 2 times x squared. Yeah, there we go. And then negative 2 times negative 3x would be a negative times a negative. So it's a positive of 6x. And then negative 2 times negative 10 is positive 20. And then we'll just put together some like terms and call it a day. This is the only x to the 3, but the x to the 2's, we do have a couple of that. And so that'd be negative 3 and negative 2 makes a minus 5x squared. And then we have negative 10x and positive 6x. We could put those together. That being a negative 10 and a positive 6, that's like a minus 4x. And then we have a plus 20 as the only constant term. And that's looking good. Something like x to the 3 minus 5x squared minus 4x plus 20. Got it. Okay. Now clearing that junk off. Now we have finding all zeros here. When it's given to you in factored form, finding zeros is no big deal for us. We'll just kind of take it in pieces. You know, what makes 3x plus 1 equals 0? What makes x plus 1 equals 0? What about x minus 3? And what about x itself? You know, we'll just do it in pieces. That's what's nice about factored form. That's why we do that. That's why we get them in effective form. And so a little bit of complication here and there. We have x minus 3. Well, positive 3 minus 3 would give that one a 0. And the x plus 1, we have negative 1 plus 1. So negative 1 zeroes that one out. Another pretty straightforward one is this x one. You could actually just shoot in a 0 because it is just a 0. It is just an x there. If it bothers you to have that there, you can always, instead of putting an x, put x minus nothing, and then 0 minus 0 works. I don't know, that might make things worse instead of better. But nonetheless, if you have just an x there, it's okay to say you could plug in 0 for it as is, and you'd get a 0. The only one that's maybe not quite as obvious, besides the weirdness of that x there, is 3x plus 1, And so you may or may not be able to look at that and tell what zeroes it out. But if you can't tell, it's okay to kind of equation solve your way there. No big deal with that. It would be like, okay, 3x plus 1, if I minus 1 off of both of those, well, then we got 3x still sitting there, but 0 minus 1 is negative 1. And then 3 times something being negative 1, that's a little weird. So then we'll divide the 3 out to tell us what to do there. And now we have x is negative 1/3. That's what I would get. If I were looking for zeros there, that's probably how I would approach it, something like that. And now we got all of these guys. Okay, next one is worse, of course. Finding zeros when things are ugly. That's where we get into our rational root theorem and stuff like that. Okay, let's see here. Clear all the drawings. Okay. But we'll try and do it fast. Things that go into the last guy is negative 1. Things that go into the very first term is 5, plus or minus of all that, and we'll just zero them out until we find them. And so things that go into negative 1, or yeah, I guess you could put negative or positive because we're doing both anyway. Things that go into it are 1, and it's a plus or a minus. Things that go into 5 is a 1 or a 5. Okay, so we have not many options here. We have a positive or negative of 1 over 1. And if none of that helps us out, we can do 1 out of 5 or 1/5. So we'll see. Hopefully, we don't have to go that way, but if we do, we do. So we'll try them out. And so remember, that's how we narrow it down. Now to try them fast, we'll just shoot one of those options up in the window and then go from there. I'm doing a positive 1 over 1, which is 1. We'll do a 5 and a 1 and a negative 5 and a negative 1. See how that goes. There we go. Bring the 5 times 1 is 5. Makes a 6. 6 times 1 is 6. That adds up to a positive 1. This just might work. Oh, look at that. First try again. Okay, we got ourselves a 1. This thing being x to the 3 function here, we're going to have 3 solutions. We just found our first one is the number 1. The other ones, well, notice this. If it was an x to the 3, and I'm technically dividing out an x minus 1 factor, if we're doing this by synthetic division, that's kind of what that represents. Yeah, there you go. Then x to the 3 divide out a x guy, we're always going to be 1 degree less in synthetic division, so this be x to the 2. So now I have 5x squared plus 6x plus 1. I'm wondering what zeros that out. Don't tell the other teachers about this, but sometimes I use that 0 to make an equal 0, even though that's not really what it's supposed to stand for. It's a remainder 0. Anyway, so then 5x squared plus 6x plus 1, this is the remaining factor. Behind the scenes, what's going on is this is, really we have x minus 1 as one of our factors, which gives us that positive 1, 0. And then here's the other factors that make a good factorization of that whole thing. That's the proper way to look at it. What we're doing so far is also just in the nuts and bolts of it. I'm looking for what makes this thing equal 0 now that I'm down to a quadratic left over. So then I'm like, can I factor this or should I quadratic formula it? I'll go ahead and do it by factoring, but quadratic formula will always work for you if you like. Actually, well, yeah, whatever. I'll do it by factoring. If you prefer quadratic formula, it's totally okay. We can always talk about doing that too. Anyway, either way is fine. And so then if I were to factor this, 5 times 1 is 5. I'm doing some kind of an AC method or grouping method at this point. 5 times 1 is 5. I need things that go into 5 that add up to 6 at this point. So that's probably 5 and 1. So that's how I'll split the 6 up, or this x term up. So we'll go 5x squared plus 5x. No, plus 5x plus 1x, and then plus 1. And then from there, we'll split that up. And so then, let's see here, common factor on the left-hand side, they both have a 5 and they both have an x. What's left is an x plus 1. Plus, on the right-hand side, probably there's nothing that goes into both except the number 1. So I'll divide out a 1, and I still have an x plus 1 left over. And there, left. So here we go. Taking out that common factor, now we have x plus 1 times 5x plus 1. And now we can find the other zeros. -1 plus -1. And then 5x plus 1, what would zero that out? That's 4. 5x plus 1, I wonder what zeros it, and I'll just kind of minus 1. And dividing the 5 will tell me kind of where I should be. X equals -1 divide 5, or -1/5, or -0. Probably don't do the decimal one. Okay, anyway, looking good. Again, if you prefer a quadratic formula with A, B, and C at that point and stuff, make sure you practiced on it, Okay, clearing this out. Finding zero, actually, believe it or not, is factorable. This is a difference of cubes, perfect cubes. If you know how to factor that, go with it. Otherwise, things that go into the last guy over things that go into the first guy. And so we'll say there's things that go into 125 over things that go in. Fortunately for us, as big a number as that is, not much goes in 5 times 5 times 5. And so things that go into it are 125. That's pretty much it. Things that go, there's 1 goes in, 2 goes in, 4 goes in, 8 goes in. And then from there, we'll try a plus or minus of things until we get some combo that works. If not, then maybe -1/1 or 5/1, or, we'll. So then let's see here. Okay, +1. And then notice here, something that we haven't done on, so we have an x to the 3 here, but there's no x to the 2. There's no regular x. We're just, so remember what that looks like is we're like, well, this is, there we go. This is 8, and then be 8x to the 3. If I write that out, squared, and plus 0x, and then minus 120. Zeros there we'll have to account for as we're doing our division. Let's make that happen. Here we go. 0 and then a -125, and see if that actually does what we want. Excuse me. 8 times 1 is 8. Times 1 is 8 again. Adds up to 8 again. Is 8 again. Row here, Supposed to add up to 0 in order. We try a -1 or something like that. Let's see here. Clear out some. Oh, actually, instead of clearing out all that mess, I guess I'll just. Apparently nothing. I guess I'll just erase these. Okay, looking pretty good. Now we'll try another one. Then if I get desperate, we'll try some other stuff. Okay. Try -1 maybe. Drop in the 8 here. -1 is not really looking promising either, to tell you the truth, because of all these zeros. It just seems like it's going to be a funky thing to make happen. And so then whatever. Anyway, so then we have -1 times 8 is -8. Adds up to -8 times -1 is +8. Adds up to 8 times -1 is -8. And that's not going to be 0 either. Not 0. Okay. So now we're desperate and we're like, great. What do I need to try here? And so then it's okay. Sometimes they go this way. You just got to be a little bit patient with it while you try some other ideas. If I were to guess at this one, just knowing stuff about them in order to kind of save time on the recording here. So I don't try all the things 5/1, -5/1, 25/1, all the things. What I might do here is knowing a little bit about how this would probably go. I'm betting you that all those over ones won't work. But what if we did like a 5/2? I'm thinking that might do it. And this would be a good demonstration in case you get an ugly one on your version of the test, just in case. Hopefully you won't. But let's see if 5/2 does it. And if not, then maybe -5/2 will. And if none of that works, then I'll start scrambling desperately. We'll see here. If we have an 8, bring the 8 down. 8 times 5 halves is going to be weird here. But remember how it goes. This is 8, essentially 8/1. And so 8/1 times 5/2, that's 8 times 5 on the top is 40/2, though. So 40/2 is actually not so bad. And then you're like, well, maybe this could work out because that's actually a whole number, you know? So that's kind of cool. And so you're like, oh, okay, so that makes a 40/2, which is 20. 0 plus 20 is 20. Okay. 20 times 5 halves. Well, watch how that goes. 5/2 times 20. Well, 2 goes into 20 10 times. So those cancel right away. Or if you don't like canceling fractions, it's okay just to be like, well, 5 times 20 is 100, and then 100 divided by 2. And that'll be 100 divided by 2, which is 50. And it's looking good because it's like promising that they're coming out to whole numbers. So that's kind of nice. Okay, we don't have any negatives, and so that's actually working to our advantage so far. 0 plus 50 is 50. 50 times 5 halves. Okay, moment of truth. Here we go. Let's do a 50 up here now. 50 times 5 halves. Okay, and I'm looking, if I were to do this my way, 2 into 50 goes 25 times, and that's actually really encouraging because 5 times 25 is 125, so that'll probably work. If you don't like doing that reducing thing, or the cross, 5 times 50, and then divide that by 2, and that is 125. That's good. Now we have 125, and -125 adds up to 0, and we got our first 0 of our 3 of them. Because it's an x to the 3, we're going to need 3 zeros. So we got our first one, that'll be the toughest one. And so 5 halves, we'll keep that on the side. We'll remember that. 1 of them, 2 of them, 3 of them. 5/2, looking good. Okay. Now what's left over, though, remember how that goes. Here, I'll take my little over 1 away, I guess. There we go. We have, if that was an x to the 3 and we divide out a single factor, a linear factor, now we have x to the 2 left over. So x squared, 8x squared plus 20x plus 50. I'm wondering what zeros that out, again, with my adopted equals 0. And now we're just trying to figure out how to go from there. And so then, we can go quadratic formula or factoring or whatever we like. I'm looking at this and I'm noticing these are all even numbers. I might just chop them in half to get smaller numbers. Um, and because dividing 0 by 2 is no big deal, and that'll just make them all smaller. But if you're not comfortable with that, maybe we'll just do it by factoring or by quadratic formula as is. And since I did it by factoring on that other one, maybe we'll do the formula on this one. So clearing up a little room, just for the sake of demonstrating your quadratic formula for you. Here we go. See if this thing does it. We're pretty close. Okay. Now, if we got a quadratic formula, that's a and then b and then c. And so then remember that's x equals -b plus or minus square root, all this stuff. So then -b is -20 plus or minus the square root is b squared, which is 20 squared, minus 4 times the a and the c number, and the a number is 8, and the c number is 50. Everything's positive, so that's nice. All over 2a, and 2 times 8 is our a term. Then we're just simplifying it from there. And so let's see here. -20 doesn't do much yet. Now we got 20 squared is 400 on the inside of that square root. So there's 400 there, minus of whatever 4 times 8 times 50 is. Let's see here. If I did 4 times 50 first, that would be 200 times 8. So then 2 times 8 is 16, so 1600. So 400 minus 1600. Yikes. Didn't expect that to happen. And now we have over 2 times 8 is 16. -20 plus or minus. I'm glad I did this by the quadratic formula because this wouldn't have factored well. 1600 is over 16. 1200 is going to be imaginary. It's not going to go well. And so remember how we break down square roots in case it's been a while. Go ahead and make some room over here now. So come on. There's no way I'm in. Okay. Roots, that 1200 in there, it will be imaginary. So there'll be the I part of it or what. That's 12 times 100 as a factorization. 10, of course. And if you want to, you can just take out a pair of 10s right there, or you can split a pair of 5s, and that'll be fine. I'm going to go ahead and take the 10s, and then 12 becomes 2 times 6. I'll circle it. And then 6 becomes a 2 times 3. And notice we have a, remember how this goes. A pair of 2s becomes a single 2 outside. A pair of 10s becomes a single 10 outside. And then what's left here that didn't pair out is the 3. Now I have a radical 3. And then 2 times 10 is 20. So now we have 20 radical 3 on the square root part. Don't forget it's imaginary. So 20 radical 3i or 20i radical 3 or something of that sort. And so then to simplify our answer, well, let's see what we got so far. We have negative 20 plus or minus 20 radical. Do this. All 3 of them, feel free to reduce it out. Some number that goes into all 3 of them. Don't do it by just a couple of them. Really, you're supposed to kind of take a common factor and then do it, but it does work this way. And so then you could say, well, 4 goes into all 3 of these guys, and 4 goes in there 5 times, 5 times, and 4 times, and that'll give you the answer we're looking for. And so we'll be like, okay, this would be 5 plus or minus, of course, 5. Oh, I guess it's a negative there, huh? Negative 5 plus or minus now a 5 radical 3i, all divided by not 16. Now we got our 2 different guides, the plus version and the minus version of that. I'm glad that I didn't do that by factoring. Cool. And so then those become the other. And then the minus 5 radical 3i version, because there's the plus. That's what I see for those ones. Cool. Clear this mess out. Not much more, guys. See what else we got. Identify the holes, the intercepts, the horizontal asymptote. Okay. If I were to see this one, remember, holes are something that make 0. There's no x minus 2 on the top or anything. So there's bottom and the top at once. So there are no holes in this one. None. For intercepts, we're looking for x-intercepts and y-intercepts. So for x, oops, y-intercept. Okay. But the x-intercepts, the y value is 0, or in other words, it's good enough to make, you can plug in to make that top be 0. It'll always be 4. Will never equal 0. Even if you get it to be 4, fine, but it won't be 0. And 4 over any other number. Or in other words, if you don't have x's to plug in up here, you're not going to get that top to be 0. No x-intercepts here, interestingly. This thing doesn't pass on it in any, well, anyway, it doesn't. And then, so we'll say that get when you just shove in a 0. So unless we go undefined here, we will at least 4 over 0 minus 2 is 4 over negative 2. 4 over negative be just negative 2. So a y-intercept at a y value. And then it asks for a horizontal asymptote. Remember about the horizontal asymptote. Oh, I shouldn't get rid of that yet. But the horizontal asymptote, maybe I'll change colors. It's good. Okay. Horizontal asymptote, that's us just analyzing. We call it the long run behavior or the end behavior of the function. It's us analyzing what happens as you plug in bigger and bigger values for x. Here's our x plug-in, and we're like, okay, if I plug in a million or a negative a million or something like that, say just a million, what happens to the output values? Do they start tapering off or do they skyrocket with it? And notice with this one, if I have higher power of x than on the bottom than I do on the top, this is an x to the 1 on the bottom, and there's no x's at all on the top, or x to the 0, x to the nothing. If that's the case, then when I plug in huge numbers for x, I think that we're about to get a doorbell wrong. I think I got away with it. Okay, I paused the recording in case this guy rang the doorbell. The dogs went nuts. Okay, anyway, so I guess without going further into it, we'll say if there's a greater power of x on the bottom than on the top, then as you plug in millions and millions on the bottom, or for the inputs, what you see with the outputs is that the outputs just keep being 4 over 1, 4 over 10, 4 over 100, 4 over 1,000, and then it keeps on being 4 out of some huge amount of pieces. And 4 out of a million is like saying I had a piece of pizza. I saved you 4 pieces, but I'm sorry, it was 4 pieces out of a million of them. And then 4 pieces out of a million pieces is almost nothing. And so that's what we say this goes to, is this does have a horizontal asymptote, but the horizontal asymptote is exactly 0. We'll say horizontal asymptote is at a y value of 0. That's what goes on with that. Okay, something similar on the next one. Clear them out. This thing factors out if we wanted to find all the intercepts and things like that. Let's see here. If I factored this out, a 2 comes out of everything, then it'll be x squared plus 2x minus 3 left over on the bottom. And then that factors out. Let's see here. I'll have a 2 and then x times x. And then things that go into negative 3 that add up to 2, that'll be plus 3 and minus 1 or something like that. And so then let's see here from there. Okay, if I wanted to find a hole in the graph, there's nothing that will zero out both the top and the bottom, because on this one, there's nothing on the top to shoot into. So there's no holes in the graph, none for the holes in the graph. For the intercepts, let's look for x-intercept and y-intercept. Same issue as last time. There's no x-intercepts. No x-intercepts, because I'll never get the top to be 0. And then the y-intercept, that happens when I shoot in 0 in for x's, so that'll be 1 over 2 times 0 squared plus 4 times 0 minus 6. And what that ends up giving you is just a bunch of zeros here, and so we have a 1 and then a minus 6. So we have a y-intercept of that. Y equals negative 1 out of 6, or 1 over negative 6, or however you want to say it. That's for our y-intercept. And then similarly, like the last one, for the horizontal asymptote, because we have a greater degree on the bottom than we do on the top, there's a higher power of x's on the bottom than on the top, then the bottom is growing higher than the top is as you plug in bigger numbers. So there will be a horizontal asymptote for sure. There will be one, but it'll be at y equals 0. We can always talk about, that stuff. Well, anyway, I'll catch you when I'm not recording something. Okay. And clear those out. And then here we go, solving a few equations here now. Now we got solving equation we got these bottoms are almost the same, but this one is 5k squared. This is 5k squared. This one's just a k squared. It doesn't have the 5. So I'd recommend timesing that by 5 so we can get all these bottoms to match. And then it's like we don't need them. What you might remember, it's like we could, if we wanted to, times everything by 5k squared over 1 and let them all cancel at that point, And so you don't have to write all that every time if you don't want. What I end up doing is just by the time I get all the bottoms to match, I just kind of let them go. And then we'll say, okay, that means we have a 1 equals k plus 2 plus just 5. And then a 7, so we have 1, and then minusing the 7 over there. We got the equals 1 take away 7 is negative 6. Looking good. let's see, here's something similar. Notice that this guy doesn't have a bottom at all. So he matches the other ones. You got to get that on the top as well. We're like, gone, gone, gone. Don't need them by the time they're done. And then we'll be like 1 equals, and then we have 3 plus 1 timesing with b minus 2, just looking at the tops. And then we'll solve that thing out, and then we have 3 plus b minus 2, because 1 distributes in there and doesn't really do much, equals 1. 3 minus 2 is a 1, so we have now that'll be a b, positive 1 equals 1, minusing the 1, minusing the 1. And now we have b equals, I guess, just 1 minus 1 is 0. Done. Looking good. Unless I messed up something. I don't think so, though. So b equals 0. Looking good. One thing you got to watch out for on these ones, just in case this happens to you during the test, is notice, okay, before I erased those bottoms there, I was hoping I'd get a chance to address this in the question, but I didn't. Notice if I have these b minus 2s on the bottom, before I canceled them, it's something that's worth noticing is if I plug in a positive 2 here, it could be all bad. So 2 minus 2 would be no good, and because it'd be a 0 on the bottom, right? And so then if you ever if you're doing one of these problems and you get a problem or an answer that says something like that, where it's like, oh, b equals 2, perfect, but that's the thing that I should not be, you know, positive 2 is an answer that it cannot be because it makes this expression undefined here and this one. If that's the case, then you're just going to have to say, well, there's no solution at all because the only thing that it should have been is what it cannot be. And so, anyway, watch out for that. The answer is not 2 here unless I messed up. But anyway, that could happen to you. So just watch out. Okay. And then last one of that sort, we'll say, well, maybe good to get some space over here, actually. Okay. I swear I'm erasing better than this. It's not catching all my cool detail work or something. Okay. So maybe I should have just cleared the whole page. That's whatever. Okay. Now notice these bottoms don't match. This one doesn't even have a bottom. This is super weird compared to that one. But if I factor it, it can be helpful. I take an A from both of them, and that gives us with an A plus 3 left over. And that gives us something to work with because this already has the A, but it doesn't have the A plus 3. So if I times it by A plus 3, then we have an A and an A plus 3. And this has an A and an A plus 3. And this one has basically nothing. So we'll need to times it by A and A plus 3. And then A and A plus 3. And then all the bottoms match. A plus 3. A plus 3, also known as that. A plus 3 times 1. So don't need the bottoms because we just got them to match. And now we'll just see what the tops look like. This is 1 times of A plus 3. Not that you need a times 1. And then equals, and then we have, let's see here, A squared minus A minus 6, and then minus of 1 timesing with all of that mess. You know what? It's A times A minus A plus 3, but it's going to be the same thing as A squared plus 3A here in a second. So I'm going to go ahead and put that. That'll be good. And then let's just see how that cleans up, I guess. 1 times anything doesn't really help. So we'll just call it A plus 3, then A squared minus A minus 6, and then minusing 1 times all that. That'll be just a minus A squared and a minus 3A. From there, I don't know, probably the best things to look together are, first off, making sure your A's don't look like a number or something. And then we have A plus 3 equals, let's see here, A squared minus A squared. That's good like terms to put together. So that's gone. A squared minus A squared, done. And then we have a minus A and a minus 3A makes for like a minus 4A minus 6 equals A plus 3. Almost done there. And then let's see how this goes. If we have a 1A here, maybe we could plus the 4A over to there. That'll work. So we have 1A and 4A makes like a 5A plus 3. And then yonder, it's like a negative 6, and it's almost done. Minus and 3 minus 3. We'll give this the old 5A equals negative 9 treatment. And then divide into 5. Now we got ourselves, I guess it's just negative 9 out of 5. And then we'll just double check that's not something that will make this thing undefined. It will be okay. And since this is an a plus 3, it looks like -3 would make it undefined, but that's nothing like what we got. So we're doing okay. So that's good. Okay. And then that actually cleaned up better than I'd feared that it might. Okay. Next thing up, clearing this mess. Two more problems. Here we go. Yeah, let's scroll that just a little bit. Oh, answer key time. Okay. Okay. Now, I told you the answer was 6. Okay. So then here we have solve the inequalities. These things are not the quadratic type inequalities. These are the irrational ones. And so they have one other element to consider that we hadn't been dealing with before. So one thing to watch out for is notice that -5 plus 5 makes this thing 0 on the top. So we'll make note of that. X equals -5 makes it equal 0. Because if you have 0 on the top, then 0 over anything gives you a 0 output. So it makes it equal 0. But x equals -2 makes it undefined. So keep that in mind. Whoops, there we go, makes it undefined. Use -2 plus 2 and make 0 on the bottom. And so those are things that are worth noting. And then we'll say, okay, number line, okay, -5 and -2, they're both kind of to the left on the number line. Because like if here were 0, then here would be the -2 and -5. Circling them, noticing this though, does equal to 0 count? It does. Equal to 0 counts. -5 makes it equal to 0, so we'll color it in. But -2 makes it undefined, and undefined is never going to count, so you never get to color that in. Then we'll handle it like we did the other inequalities before, and we'll try something on the left, and try something in the middle, and we'll try something on the right. And so here we go, real quick. We try something on the left of -5. We could try maybe -6 or something. And then if we tried something between -2 and -5, pick your favorite. -3 and -4 is a good choice. I'm trying -3 and then try something to the right of -2. I'll probably just do 0. I'm going to go ahead and color switch that so it stands out in the mess. Now, if we try a -6, that's -6 plus 5. And then a -6 plus 2. Uh, Embarrassing. There we go. -6 plus 2. And we'll see how that all goes. -6 plus 5 is -1. -6 plus 2 is like -4. And that's a negative into a negative. It's a positive. And then we're like, is that what we're looking for? Well, it's asking us to find outputs that are less than 0. And we found a positive that is not less than 0. So no, not doing what we want here. Let's see if the middle does. The -3. -3 plus 5. -3 plus 2. And then let's see here, -3 plus 5 is +2. -3 plus 2 is -1. We have a 2 divided by -1. That is -2 by the time you're done. Positive divided by a negative. That is less than 0 because it's negative, and that does what we're looking for. So that's good. That gets colored in. And then finally, we'll try something on the right. 0 is our friend. So 0 plus 5, 0 plus 2. That's going to be a +5 and a +2. There's nothing negative about this, so it is not going to be less than 0. So nothing on the right does what we want. So for number 32, it looks like we have colored in the 5, negative, and we colored in between the 2 and the 5, and that was the end of it. Nothing out to the infinities, nothing out to the sides. So we'll say something like color in from -5, stop when you get to -2, but don't count the -2. That looks pretty good for that one. Okay, this other one is a little bit more effort. Check this out. A little bit more effort on this one. I'm going to go ahead and clear those out. Okay, on this one, you notice that we're not comparing it to 0. It's not like that's necessary, but it does make things helpful. It makes them easier to deal with. So since that is not being compared to 0, I'll probably start by getting it compared to 0. Instead of a less than 3 thing, we'll make it a less than 0 thing if we can get a way to do that. And so easy way to do it is just to be like, well, if it's a -3, I'll put a +3. -3 on the bottom to both sides. My plus looked better, but whatever, +3. And now we have negative less than or equal to 0. Okay. Doesn't look good yet, but we are the analysis a little bit easier and more obvious. But there's a little bit of cleanup that'll make it that's because now this is not one fraction, it's two different entities, a fraction and a whole number. So I'm going to go ahead and get these bottoms to match. Put a times of x minus 3 there, times x minus 3. And then let's see how this goes. Now we have, they're both over x minus 3, so it'll be something over x minus 3. And then the something will be a negative x take away 3 plus of 3 timesing with x minus 3. That'll be our top here. So then let's see how that translates by the time we're done. That's going to be negative x, and then we'll see how that's plus 3x, right? 3 times x. Here, instead of doing a bunch of stuff in my head, we'll just do it together. So it'll be negative x minus 3 plus 3x, and then 3 times negative 3 is a minus 9 all over that x minus 3. So then we're like negative 1x plus 3x is like 2x, and then minus 3 and minus 9 makes minus 12 all over x take away 3. Looking good. And now we have a better version, a more friendly version of our inequality in both ways. It's comparing things to 0 again, and it is one nice, just one fraction again. So we're going to keep that as our new version of the inequality as we proceed. We'll keep that around. I'm going to go ahead and clear some of this other junk off just so we have, room to work. Let's not forget where we came from on that. Okay. I'd like to see you try and tell me that I didn't hit all those things. We'll see what it says this time. They're pretty close. Okay. Now, here we go. Okay, 2x minus 12. What makes that equal 0? I'm looking at that as probably a 6. But if it's not, it doesn't mean that you just kind of can see that that's a 6. So we're looking for what makes the 2x minus 12 equal 0? What makes x minus 3 be 0? Well, that'll be probably a 3. 3 minus 3, And so we'll make note of that. And we'll say if I plug in a 3, x equals 3, positive 3, that's going to make this thing undefined. Makes it undefined. Just whatever. It's supposed to say undefined. Okay. I've got to stop trying to put the cursive in there. Okay, and then 2x minus 12. Well, okay. We can, if you're not sure how that'll go, you can always just kind of solve it equation style, It'd be like 2x equals positive 12, and then dividing it out, then you probably see the 6 that we were talking about, Then we got x equals 6. No big deal. But what that does is make the top equal 0. So then we'll say x equals 6 makes it, I still keep doing the cursive. It's okay. We're just going to keep doing it, I guess. Makes it equal 0 because it makes the top 0, So then x equals 3 makes it undefined. X equals 6 makes it equal 0. Okay. Then we'll keep those things in mind as we're number lining it. If here were a 0, then we have a 3 over here somewhere and a 6 over here somewhere. And we're going to try things to the left and to the middle and to the right. Probably end up erasing some of that mess in a second, but for right now, I guess we'll just kind of color change it. Okay. So then trying things to the left and the middle and the right, something to the left of 3, we could try it 2. Or, what might be even better is just a 0 is to the left of 3. And then we could try something between 3 and 6. It'd be like a 4 or a 5. I'll try a 4, I guess. And then, although 5 is nicer to work with. And then try something to the right of 6. I guess we'll do 7, So here we go. And remember, we have a new version of our inequality to work with. That's what probably we'll want to do because the other one is ugly enough and it'd be harder to analyze. Because it's hard to know when things are less than -3 when you have a fraction and stuff, Not that big a deal, but whatever. Okay. Okay. Plug in junk in, something left of 3 is 0, so we'll shoot in a 0 there. That'll be easy enough. 2 times 0 minus 12. And then, of course, 0 minus 3. That's perfect for us because that's just going to be negative 12 over negative 3. Both negatives, that's a negative into a negative, is a positive. 12 divided by 3 is 4. But more important than that is a positive, and that is not less than 0. Not what we're looking for. Nope. Okay. Maybe we'll be able to just keep this stuff. And then a 4, we'll shoot a 4 in there. That's between the two of them. 2 times 4 minus 12. And then we have a 4 minus 3. And notice that the top is going to be negative still because the 4 is not big enough to make that become a positive. It's be 2 times 4. It's 8 minus 12. 8 minus 12 is whatever that is, negative 4. And then 4 minus 3, though, is going to be positive because it is bigger than the 3. So then that'd be a positive. So whatever. That, I guess I say too much at times. Anyway, 8 minus 12, 4 minus 3. We got a 4 and then 1, and it's a negative divided by a positive. That's the kicker, though, of course. This is a negative here. However you slice it. 4 divided by 1 is easy, but it's a negative, and that means it is less than 0. So these things do what we want them to do. It's another one of these in-between ones so far. Let's see what happens on the next part. Now we'll try a 7. 2 times 7 minus 12, and then 7 minus 3. And then let's see how that goes. It's 14 minus 12 would be a 2, positive. And then 7 minus 3 would be a 4, positive, and nothing negative about it. 2/4 is like a half, but it's more than anything else that is a positive. So then I guess we'll just say that is not less than 0. No. And then we'll state our answer as such. We'll say in our funny magenta color. Oh, wait, I didn't color in the things that need to get colored in. Equal to 0 count here, yes. So 3, I still won't be able to do because that makes it undefined, but 6 I will be able to do. Okay, so we'll color in the 6 and we'll color in between them. Okay, that works. Here comes the magenta again. Color in the 6, color in between them. And that's what we'll do for our interval notation. We'll say start from 3, go until you hit 6, count the 6. Call it a day. And that's how the cookie bounces.